So we're now going into the topic of integration. So we sort of, in the last topic, we did the fundamental theorem of calculus, and we looked at definite integrals. Now, part of this next bit is where we're looking at indefinite integration, or we just call them integrals for this form. So just as to help us link to this next topic, we're looking at, well, previously the antiderivative of x squared was a third x cubed. So that meant that if we had a function that was a third x cubed plus a constant, it had the derivative of x squared. So in this space, if I had an integral of x squared dx, I'm just going to use a and b here. So we're going to link that to, actually maybe I'll use what we used in fundamental theorem of calculus. So a is just a point. This would be the antiderivative of x minus f of a, which would give us the antiderivative of x squared we've worked out is 1/3 x cubed minus 1/3 a cubed. So that's from our last topic. Now, our new thing that we're looking at here is, well, if we don't put these bounds on here, realistically, if we take the integral of this, we're always going to get this sort of area function here, this antiderivative x. And then we're going to get this constant, which is just this extra value. Now, the constant could be anything here. We've sort of come up with this link between the two. So we're not looking at having the direct bounds anymore. We're looking at, well, I could do this indefinite integral here, and because I know that the antiderivative of x squared, I'm going to get rid of these bounds here as well. The indefinite integral, if I take the integral of x squared, I'm just going to get 1/3 x cubed, and then I just go plus a constant. So those values are equal. All right. Now, there's a couple of rules here, which are from our text. These actually are going to be super handy in helping us simplify these. So I'm going to just keep rolling here. So the idea is, in this first bit, we're looking at sometimes if we take an integral of something, we can actually figure out, if we take the derivative of something, we can then figure out the integral. So if we look at this f of x equals x to the 4, if I take the derivative of this, f dash of x is going to equal 4x cubed. Now, because the process of finding the derivative goes this way, the antiderivative or the integral goes the other way. So that means that if I go, well, I want to figure out the integral of 4x cubed with respect to x, then it is going to be x to the power of 4 plus some constant. Now, that is because if I'd taken the derivative of this with any constant, I would have had it. So pretty much any integral now we're going to do, we're always going to have the constant. So let's look at this next one here. Similar thing we're going to practice. Well, if I have a square root, I do the derivative of this. So you got to remember that the square root is x to the half. The derivative of this would be half x to the negative a half, which would equal half square root x on the denominator. So a little bit messy there. Let me try and clean that up a bit. Okay, so a little bit messy, but that's fine. So this would mean here, if I was to flip this around, I could go, well, how good is this? I've got 1 over 2 root x with respect to x is going to give me the integral of this would be, well, x to the half plus c. And so it's quite handy to find integrals this way, and sometimes we can actually do quite complex integrals if we can do it. Now, in our course, our range of integrals isn't as big as our derivatives, but if we found the derivative of something, we should be able to go the way back. So I'm looking at the example in the text now because this is a good example of where we can use this. It goes, if we have a function y equals x to the power of 4 plus 2x squared, find dy dx, hence. Now, hence is like in a test question. It means use this bit before it and find the integral of 2x cubed plus 3x squared dx. So let's find dy dx first. So dy dx here would equal 4x cubed, so the integral of this first one here, plus 2 2x to the 1, which means we're going to have 4x cubed plus 4x. Okay, I've stuffed up because this was actually meant to be a cubed, which means that it changes our function a little bit in that we should have, this should be a cubed and a squared. All right, and then let's change that to a 6. Now, you'll notice here that this has a common factor of 2. So we've got 2 times 2x cubed plus 3x squared. So we found the derivative of that. Now, let's look at this integral here. This means here the integral, this is the integral we're looking at. So let's just think about this, the integral of, I'm going to pick this one here. It's just simpler to start with. So we've got the integral here of 4x cubed plus 6x squared dx. And we know that this equals our original function here of x to the 4 plus 2x cubed. So we can actually put that on this other side here. So x to the 4 plus 2x cubed, and then just plus a constant there. Now, this makes our next step interesting because you'll notice that this is close, but it's not quite our integral. So what we can do is we can go, well, let's do the integral, and I'll pull out that common factor of 2 that we talked about, and we get 2x cubed plus 3x squared dx, and this still just equals x to the 4 plus 2x cubed plus c. Now, this is pretty important because there's 2 out the front. If we go back up to our rules that I said were important, we've got this rule here. Oh, I should have, I'm going to get rid of that just because it looks a bit like a negative. Okay, so you notice here, if we have a constant here, we can actually pull that out of the front of the integral. And we looked at that in the last section we looked at. But that means that here, this integral here, 2 by, and then we've got, I pulled the 2 to the other side of the integral sign, so it's not inside the integral anymore. 2x cubed plus 3x squared dx equals x to the 4 plus 2x cubed plus c. Now, this is pretty close to the integral we were looking to find. We're now at a stage that we've got this. The only thing is this integral is multiplied by 2. So we need to consider, well, what's the inverse of 2? And it is to times by a half. So something multiplied by a half, we would multiply by 2, we would either multiply by a half or divide by 2, either or is the same. I'm just doing the times by a half because it allows us to see it outside of the integral. So that would get rid of this, so the integral is not doubled anymore. And we would have, well, this means that the integral of 2x cubed plus 3x squared dx is going to equal x to the power of 4 on 2 plus x cubed plus, so x cubed is because this 2 here is multiplied with this one and then it's multiplied with this one. Now the interesting thing is for the c, we still just count it as a c, even though that now this step should be c on 2. But because we don't know what that constant is yet and we're not really too worried, it's just a constant, we just leave it as a c. And we're finished solving that, so that's a good one there. Let's just quickly do our next one here. So the next so that example helps us get through the simple ones. Then the next example here, we're looking at find the dy dx again. So we've got 5x minus 1 to the half. So let's do the integral of this. We get dy dx equals half 5x take 1 to the negative a half, and then we've got obviously a chain rule that we've got the derivative of the inside is going to be 5. So this is going to equal 5 on 2, and it's going to be over 5x take 1. So I'm going to get a bit lazy. I'm going to drag this over. So if I put this over here, and we get rid of this, this means that if I do the integral of this thing by dx, it's going to equal our original function, which was square root 5x take 1 plus c. Now, this is pretty good at the moment, but we've got to get rid of, you'll notice the difference in these functions is that I've got this 5 and 2 here. So same with that rule before, we can, if we have a constant, we can pull it out the front. So if I pull this out the front, I'm going to get 5 on 2 integral, and it's going to end up being 1 over square root 5x take 1 dx, and that equals square root 5x take 1 plus c. I've now got, well, if I can think of something to multiply to get rid of this, I've got the integral I want. So what I do is I go, well, I'm going to times this by 2 on 5, which means I multiply this side here by 2 on 5. So that means my next line here, I've got the integral of 1 over 5x take 1 with respect to x is going to be equal to 2 root 5x take 1 all over 5 plus c. Now, I would multiply this in, but because we don't know what the c is and we're not really fussed, it's just an arbitrary constant. It's just saying that we're adding or taking a value from it. That's fine, and that is our solution there. All right, thanks, guys.